Data moves globally in milliseconds. Algorithms map the human genome, and AI answers complex queries before we can finish typing. 250 years ago, information moved exactly as fast as a horse could run. Harvesting a single acre of wheat required days of backbreaking manual labor, and the deep winter isolated entire communities behind uncrossable terrain. The pushback against those natural limits started with observation. In 1752, Benjamin Franklin tied a metal key to a kite string during a storm to prove lightning was electrical. He applied that theory by mounting iron rods atop colonial buildings, giving million-volt strikes a harmless path directly into the ground. Until that point, severe weather was an unavoidable hazard you simply endured. Franklin proved that with applied science, humans could actively redirect nature's most violent forces. In the late 1700s, the young American economy relied heavily on agriculture, but processing raw crops by hand restricted growth. A worker could spend an entire day separating just 1 pound of cotton fiber from its seeds. This wooden mechanism is Eli Whitney's 1794 cotton gin. By turning the side wheel, metal teeth pass through a slotted wooden comb, pulling the soft fibers through while blocking the larger hard seeds. 3 years later, Whitney tackled manufacturing. At the time, muskets were built one by skilled blacksmiths. If a trigger broke, a new one had to be custom forged to fit that exact weapon. Whitney devised a system where every geometric part was cut to identical, standardized measurements. Because every piece was the same shape, a broken musket could be repaired instantly by swapping in a spare part, eliminating custom blacksmithing. This philosophy of mechanization expanded outward. By 1807, Robert Fulton mounted steam engines on riverboats to push heavy cargo against the current. In 1831, Cyrus McCormick's horse-drawn mechanical reaper allowed farmers to harvest grain at 5 times the speed of a hand scythe. By engineering machines that could outpace human muscle and river currents, the United States built the framework for an industrial economy that spanned the continent. As physical cargo moved faster on steam trains and riverboats, a new bottleneck emerged. A train carrying goods could easily outpace the paper manifests and letters sent to coordinate them. In the 1840s, Samuel Morse focused on using electrical currents to solve this logistical delay, developing a method to send coded signals across copper wire. Looking at the internal layout of this 1844 telegraph, you can see 2 prominent electromagnetic coils positioned directly below a heavy mechanical lever arm. When an operator on the other end of the line presses their key, it closes the electrical circuit. The sudden charge magnetizes the coils, pulling the lever arm downward to press an inked wheel against a moving strip of paper. 32 years later, Alexander Graham Bell realized that instead of interrupting a current to make taps and clicks, he could use a continuous electrical current to replicate the complex wave frequencies of the human voice. Messages no longer needed to be carried in leather pouches on horseback. Complex instructions, news reports, and personal conversations could now travel hundreds of miles in fractions of a second. By the late 19th century, inventors turned their attention toward capturing elements of life that had always been fleeting. Thomas Edison achieved this with sound in 1877. His phonograph used a vibrating stylus to etch audio waveforms into a rotating cylinder, allowing a spoken sentence or a piece of music to be played back long after the room had gone quiet. 2 years later, Edison tackled light. Inside the vacuum-sealed glass of this early bulb sits a fragile filament. Passing electricity through it produced a steady glow, allowing factories and cities to operate safely long after sunset. At the turn of the century, Orville and Wilbur Wright focused on the most persistent physical boundary of all: gravity. In December 1903, on a North Carolina beach, their gasoline-powered biplane generated enough thrust from 2 spinning propellers to lift a human being into the air, achieving the first sustained, controlled flight. Shortly after, Henry Ford reorganized automobile production by introducing the moving assembly line, bringing the car to the worker rather than the worker to the car, and scaling output to levels that made vehicles accessible to the middle class. And in the 1950s, Dr. Jonas Salk expanded this systematic problem-solving into global health, developing a polio vaccine that shielded millions of children from a paralyzing virus. In a single lifetime, American engineering had illuminated the night, mechanized mass transit, achieved human flight, and engineered a defense against diseases. As the physical world became heavily mapped and industrialized, the frontier for exploration shifted from terrestrial geography to the invisible realms of code and data. Decades of government and academic research culminated in the Internet, a decentralized network architecture that allowed millions of computers across the globe to share massive databases of human knowledge simultaneously. In 2007, the release of the iPhone condensed the power of that entire global network into a glass and metal rectangle small enough to fit inside a pocket. The geographic barriers to information dissolved completely. Anyone with a device now held immediate access to libraries, global markets, and real-time communication from almost anywhere on Earth. Today, the boundaries being pushed lie at the extreme edges of scale, the vastness of deep space, and the microscopic sequencing of human biology. Aerospace companies like SpaceX developed rocket boosters capable of launching payloads into orbit, returning to Earth, and landing vertically to be used again, drastically lowering the financial cost of space exploration. In biotechnology, scientists developed mRNA vaccines that act like biological software, delivering a temporary genetic instruction manual to human cells so they can rapidly build defenses against novel viruses. We've traded wooden gears for silicon microchips and steam power for reusable rocketry, but the core mechanic of the last 2.5 centuries remains the same: an enduring refusal to accept the physical limits of the world exactly as we found it.